Our discussion is on statically indeterminate members. So when we say that member is statically indeterminate, when the reactive forces or the internal resisting forces over a cross-section exceed the number of independent equations of equilibrium, the structure is said to be statically indeterminate. These cases require the use of additional relations that depend on the elastic deformation in the members. So for this problem, we have a first problem for statically indeterminate members. Try to solve for using the equation for deformation. So problem number 1 states that a steel bar 50 mm in diameter and 2 meters long is surrounded by a shell of a cast iron 5 mm thick. Compute the load that will compress the combined bar, a total of 0.8 mm in the length of 2 meters. For steel, our E is 200 gigapascal. For the cast iron, E is 100 gigapascal. So we have here the illustration. So we have here a steel bar wherein it has a cast iron, a thickness of 5 mm, and a steel bar had a diameter of 50 mm. So the outside diameter is 60 mm, the inside diameter is 50 mm. So, of course, we're going to make use of our equation, which is deformation is equal to PL all over AE. So, based on our given problem, our deformation is equal to 0.8 mm, and the deformation on the cast iron is equal to the deformation also on the steel, and that is equivalent to 0.8 mm. So if we're going to make use of the formula PL all over AE, so we can substitute the given values. So we start with the deformation on the cast iron. So we have here our unknown P, which is the load on the force on the cast iron multiplied to the L, which is 2000 L over the area of the steel bar, which is pi d squared all over 4. And since our we have an inside and outside diameter, so we have 60 squared outside diameter minus our inside diameter. Then multiply this one to the E, which is for the cast iron, we are given with 100 gigapascal, or that is 100,000. And if we try to simplify this one, we can have the value for our force on the cast iron, and that is equal to 11,000 pi Newton. So we have now our value for our cast iron. Then for our steel, for the steel deformation on the steel, we have the force on the steel times 2000, which is the length of the steel bar, then all over pi d squared all over 4, so the inside diameter is equal to 50. The diameter of the steel bar, of course, is 50 mm. So we substitute that one to the equation. Then multiply to the E. Our E for the steel is 200 gigapascal. So if we try to, of course, the deformation of the steel is 0.8. So if we try to cross multiply, we try to simplify, we can get the value for the force on the steel, which has 50,000 pi Newton. Now we have the force on the cast iron and on the steel, so therefore we can get the value for the total force applied on the steel bar. What will be the equivalent value for the total force applied on the steel bar. So therefore, if we try to get the value for the total force applied on the steel bar, so therefore we can have the summation of forces vertical equal to 0. So total force P, or the applied force P, is equal to the force on the cast iron plus the force on the steel. We simply have to substitute the value, which is 11,000 and 50,000, and that gives us 61,000 pi Newton, or that can be equivalent to 191.64 kilonewton. Okay, the second problem, a reinforced concrete column 200 mm in diameter is designed to carry an axial load, compressive load of 300 kilonewton. Determine the required area of the reinforcing steel if the allowable stresses are 6 megapascal and 120 megapascal for the concrete and steel respectively. Use E for concrete, which has 14 gigapascal, and E for steel, which has 200 gigapascal. So for this, of course, we can have the relationship that the deformation on the concrete is equal to the deformation on the steel, and of course, based on our formula, which is PL all over AE, this is for the concrete, and this is PL all over AE for the steel. And of course, P all over A is equivalent to stress. And so we can simplify our formula for our deformation as sigma L all over A for the concrete, and we have sigma L all over A for the steel. And if we try to substitute the value for our modulus of elasticity, which is 14,000 for our concrete, and we have 200,000 for our steel, so we can simply cancel out our L. So if we try to simplify this one, we have now the value that 100 sigma for the concrete is equal to 7 sigma for the steel, or in other words, 100 stress for the concrete is equal to the 7 stress of the steel. So we're going to check the stresses on the concrete and on the steel. So we are given with the allowable stress for our concrete, which is 6 megapascal, and for the steel, which is 120 megapascal. So therefore, if we try to investigate the stress of the concrete, so we simply have to substitute the value for the steel, which is 120 megapascal, to this equation. So we have now our equation, which is 100 stress on the concrete is equal to 7 times 120. So if we try to simplify this one, we get the value for the stress on the concrete, which is 8.4 megapascal. So based on the given allowable stress for the concrete, which is 6 megapascal, so therefore this value is not okay, since it exceeds to the allowable stress of the concrete that is given on the problem. So we have here a remark which is not okay. Now we try to investigate the stress on the steel. So for the stress on the steel, we simply have to substitute the value using also this equation. We use this equation. We try to substitute the value to the equation 100 times 6, which is the allowable stress on the steel, is equal to allowable stress on the concrete is equal to 7 stress on the steel. So if we try to simplify this one, we get the value for the stress on the steel, which is 85.71 megapascal. So if we try to compare this to the allowable stress on the steel that is given on the problem, so this is smaller compared to the allowable value of the stress of the steel. So therefore, we have a remarks which is okay. So therefore, compute now for the area. So we're going to compute now for the area. So we simply have to substitute our values. So we're going to make use for the stress of the concrete, which has 6 megapascal. The allowable stress, we're going to make use that one instead of the computed value, since it exceeds with the allowable stress of the concrete. So you make use of 6 megapascal. And for the stress on the steel, we are going to make use 85.71 megapascal. So therefore, if we try to substitute now to our equation, which is summation of vertical forces equal to 0. So you have here our force on the steel plus force on the concrete is equal to 300 kilonewton. So we have here the applied load, which is 300 kilonewton. So therefore, if we try to substitute using the equation, stress is equal to P all over A. So we can have P is equal to stress times the area. So therefore, you have now stress on the steel times area on the steel plus stress on the concrete plus area on the concrete is equal to 300. So we make use, we substitute now the values. So we have 85.71 times area of the steel plus we have 6, which is the stress on the concrete, times pi d squared all over 4. So we have here our outside diameter, which is 200, minus the area of the steel equal to 300 times 1000. We have converted our 300 to kilonewton to Newton. So we multiply this by 1000. So therefore, if we try to simplify this equation, we get the value of 79.71 area of the steel plus you have 60,000 pi, which is equivalent now to 300,000. Upon simplification, you have now the value for the area of the steel, which is unknown, 1,398.9 mm squared. Okay, problem number 3. The lower ends of the 3 bars shown in the figure are the same level before the uniform rigid block weighing 40 kips is attached. Each steel bar has a length of 3 feet and area of 1 inches squared, and A is 29 times 10 to the 6 psi. For the bronze bar, the area is 1.5 inches squared and A is 12 times 10 to the 6 psi. Determine the length of the bronze bar so that the load on each steel bar is twice the load on the bronze bar, and the length of the bronze bar that will make the steel stress twice the bronze stress. So we are given with our figure, so we have to take note that the load on the steel bar is twice the load on the bronze, and the stress on the steel bar is twice the stress on the bronze. So therefore, if we're going to have the condition, so based on our given problem, that the load on the steel bar is twice the load on the bronze, and if we try to have our equations of equilibrium, summation force vertical equal to 0, we have to take note that on our free body diagram, we have the load acting or the forces acting for the steel, we have the bronze, we have the steel, and of course we have the weight of the our weight, which is equivalent to 40 kips.